So this secondment has been a collaboration between the urban design team in Perkins+Will and the data engineering group at University of Cambridge. And the research project that we are presenting today, which is called High Growth Environments and Their Potential to Become Zero Carbon Communities, is sort of the last step in the industrial secondment process that we've undertaken. So within the project, we have two main research questions. On the economic layer, one is trying to understand the evolving patterns of these high growth communities within our cities. And then in relation to the built environment of these communities, what we are trying is to identify feasible pathways for them to become zero carbon areas. But we probably need to explain some of the concepts that are mentioned in these questions. So what we mean by high growth communities, these are clusters of companies that have been identified as high growth or ambitious through an 8 trigger criteria. And this is a data set that is coming from Perkins+Will. Then when we are talking about the built environment layer, we are including all the information from the energy performance certificates. So we are using both ratings, but also the recommendations included in the EPCs. And finally, why we have used communities as a spatial unit is because we believe that business areas in the cities are shaped by interactions between companies and don't really relate to specific administrative levels or boundaries. And this is a bit of a summary of the workflow that we've created to answer these questions. So on the economic layer, first we are going to identify or detect these communities. Then we are going to gather information to describe them. So we are able at the last step to create a dictionary of typologies. So group of communities that have similar characteristics. And in parallel, on the built environment layer, we first are going to go through an exploration of association rules coming from the APCs at the whole UK. So we are able to identify underlying patterns or structures in within these rules. And then we will scale down this analysis to the specific communities. So we are able to identify the specific pathway to become zero carbon for each specific community. So going on with the first layer, this is the coverage of the data set that we have on high growth companies. And the research project has been focused on the area between Oxford, Cambridge, and Norwich. And this is mainly because Perkins+Will right now has different projects going on across this geography. So we thought that the research exercise will be more helpful for us. And in the slide, you can also see all the different metrics that we have from these companies. And we have highlighted the ones that have been used in the research, in this specific research. So first, we start constructing a network of these high growth companies. And we do so by following two conditions of attraction. So a company creates linkages to already existing companies that are within a radius of 400 meters, which is 5 minutes walking. So that's how we are somehow defining attraction between companies in this research piece. So once we have our network, we applied a community detection algorithm called walk trap, which is based on random walk theory. And we were able to identify up to 24 mature high growth communities in this area. And again, we have highlighted the ones where Perkins+Will is currently working or have worked in the past. So we have clients on these communities. Once the communities have been identified, then we need to describe them. So to do so, we select 8 variables. So it's the list that you have on the left of the slide. However, due to differences in lifetime and size of the communities, we needed to create a normalized pattern of a normalized development pattern for these communities. So we are able to fit in some of these variables. For instance, the ones related with the rhythm of growth of the communities or the ones related to the types of linkages within these communities, and being able to compare in these ways communities. So I think we need to explain with a bit more detail how we define these typologies of linkages in the communities. So first of all, we select 3 variables to describe these links. And these 3 variables are the date when the first company joined the community, the time difference till the second company joined the community, and the industrial similarity between both companies. So then, in order to identify groups or clusters within these linkages, based on these 3 variables, we applied an unsupervised learning process, which is called self-organizing maps. And the process basically what it does is you feed data into the map through a series of iterations, and at the end of the process, each of the cells, each of the node maps, is somehow representative of a group of entries in your data. That in our case will be the linkages between companies and the characteristics and these 3 characteristics. So then we can cluster these nodes from the map and their respective linkages, and we can come up with 3 different typologies or clusters of linkages. So that are the mean variables within these groups are shown in the bar chart in the middle of the slide. And the 3 typologies that we have identified is a first group that is representing recent industry specialization links, a second group that is including links of middle stage diversification, and a final cluster that is including early specialization links. So now with that information, we are able to somehow fill in these 3 last variables. And then we have all the information we wanted to have around these communities. And we can identify emerging clusters through a simple principal component analysis. And then we kind of set or create those clusters or groups through a hierarchical clustering algorithm. And finally, in creating that dictionary of typologies for these communities, these are our 4 last typologies, and this is how they are performing in relation to the 8 variables that we set to describe these communities. And what we've done is, like, for each of the typologies, we have selected a representative community where Perkins+Will is working. So this whole exercise is able to give us some insight when we are working with our clients, and we understand how this employment location, because most of them are employment locations, how they are performing in relation to each other. And now Minda is going to explain on the built environment layer.
Okay, so thank you, Andrea. So to bring the energy efficiency and built environment information in, we're using the non-domestic EPCs and focusing on the business and offices ones. So as we know, like from 2008, it is required for buildings that are on sale, rent, or construction to have an EPC. So we present of the whole built environment here. So first of all, we plot back those energy efficiency ratings to or detected communities. So first, we can see that the variations among those detected communities are quite big and obvious. Andrea, next one. Yeah, so to deal with EPC information, we're mainly using the recommendations that comes along with every EPC for the improvement. So we're using the association rule learning. So it is a rule-based machine learning method currently mainly applied in market basket analysis, web usage mining, or bioinformatics. So for example, like a market analysis would be, so if in the supermarket, if a butter and bread is purchased, the customer tends to buy milk as well. So this is kind of like a rule. And a classical example has been discovered. It's like beer and diet, baby that's all purchased together, which is an interesting bundle. So this is kind of discovered by the association rule learning process. And as analogy, so for our EPC analysis for the recommendations, so one rule can be, say, if it is recommended to add time controlled heating system, and it also recommends considering installing a ground source heat pump. So it might also recommend to us like to add weather compensation controls to the heating system as well. So this is kind of the rule in our analysis. And with association rule learning, there are several concepts that, for example, we have indicators about how frequently the items appears in the data set, or how confident we are about the rules, or how things are dependent within the rules. So with those measures, we can help to select the thing interested in. So we're exploring the whole general UK B1 recommendation structure. So we can see that several sections are coming up naturally, focusing on lightning part, renewable part, building envelope part, or heatings. And we can also explore the relationships between them within this rule structure here. And come to the previous one, please, Andrea.
Sorry.
And no worries. So if you're focusing on the one case here for the Cambridge Science Park, yeah, here. So different from the general case, we can see that we have a clear solar renewable resources part here, and we have a main problem is discovered in the science park buildings, and then there are some easy to fix problems about the lighting section here. So we're thinking like combining those findings, we can easily come up with some concrete zero carbon pathways for the Cambridge Science Park area. And then after some explorations, we have found some initial relationship. The industry similarity is higher than the rule structure tends to be more concise, or if the industry similarity is lower in the Newton Park case, so the structure can be much more complicated. But like these things are to be justified in our later work. Next one, Andrea. Yeah, so combining all those results together, we can have a profile for the, say, for Cambridge Science Park as an example, both from the business side and from the energy efficiency side. And some, but like this work is not done yet. So this is just a current phase. We are considering, because we can see like some of the results are kind of qualitative here. So first step would be to quantify the outcome of the with, say, like payback time or CO2 impact by some recommendations to help to build up a prioritization flow work that can select concrete zero carbon pathways for communities based on optimizing. We also explore more relationships between business characteristics and built environment of the resulting communities. In the end, we would like to merging can provide some suggestions for the emerging communities for further development and information on the potential policies. I think that's it for us. Thank you very much, guys. Andrea, are you still here?
Thank you, Minda.
Yeah, thank you.